I'm going to take for granted that most listeners are not jazz improvisationalists, or frankly, any musical improvisationalists of any kind. I certainly got that wrong. For some of you, apologies. Let's just roll with it. Maybe you know a little music theory, the blues scale, different modes, what have you. But when I sit down to see a true improviser, they're doing something I can't. They're doing something I can't even really totally comprehend. It's too fast for a guy like me who reads music. And from what I've been able to read, most of it's just random walk kind of stuff anyways. Maybe a known hook or two thrown in there here and there. But it sounds awfully complex to me. A very complex function. That musician is completely a black box to me. How they take the input of the other players and output the fingering, embouchure, and pressure to make the sound of the instrument, I don't know. But I do know that if I took the time to get lessons and all that, the teacher's going to break that down. There are no black box lessons. They'll teach you how to do that skill, and they'll teach it to you in a context. In fact, if your teacher does say, "Oh, it's just a black box, you can't learn it," it's probably time to get a new teacher. So it really begs the question, do we use black boxes because they're necessary, or just because that's what we got? This week on Data Skeptic Interpretability, I chat with Cynthia Rudin about some fascinating work she's done right along these lines, in a contest specifically designed to have black box models and then see how they can be interpreted. Seems like nobody begged the first question, except for Cynthia and her team.
My name is Cynthia Rudin, and I'm a professor of computer science, electrical and computer engineering, and statistical science at Duke University.
Well, thank you so much for joining us today. I asked you on to talk about, some specifics within that field, but broadly speaking, could you set a context for what your research interests are?
Well, I work in interpretable machine learning, and the goal of interpretable machine learning is to design machine learning models that are understandable to human experts. And that is different than the typical black box models that machine learning is famous for. You usually think of machine learning as generating these super complicated functions that no human could possibly understand, and these magical predictions that are being made. But that doesn't really work for high stakes decisions. For high stakes decisions, we want to actually be able to understand how these predictions are being made and be able to challenge them. And so we need machine learning models that humans can understand.
Could you give me maybe an example or two of those high-stakes decisions?
Sure, pretty much anything in healthcare. So one of the projects that I worked on is seizures in patients who are in the intensive care units at hospitals. And for these patients, you don't want some complicated function coming in and saying, okay, this patient can be taken off monitoring now, or this patient needs to have extra drugs given to them, or something like that. You really want a doctor to be able to look at a model and figure out what information that is not in the database that they can combine with this model to give the patient the best possible care. Yeah, we want everyone sort of on board with whatever decision is made. We don't want the algorithm making the decision. We want the human making the decision with the help of data and the algorithms. Another example is in the criminal justice system. So we've been looking at some of the models that are used in criminal justice, and there's at least one model out there that's very widely used that is proprietary, and nobody can understand what its calculations are, or at least the people who are being judged can't look at the calculations of the model. And in some cases, there have been typographical errors and other problems that have led to people being denied parole unnecessarily. Years of extra prison time because of a typo. And some of these problems could really be averted if people could understand the models that they're working with. And what we found was that interpretable models don't lose any accuracy over black box models for these criminal justice problems. So there's not really any real good reason not to use interpretable models for criminal justice.
Yeah, I do want to get more into, that central thesis, but I would like to pause for a moment and unpack that comment you'd made that I think comes from some of your other research. I read another paper where you're talking about these cases where those typos were actually potentially more impactful than some of the features that the other analysis was looking at. Could you unpack a little bit about your learnings there?
Yeah, we found all these cases of people with very long criminal histories that had very low COMPAS scores. So COMPAS is this model that's used in the justice system. And there's no really good way to explain it. It just doesn't doesn't seem to make any sense other than some weird data errors. I mean, you could try to think of how this could be possible, but the truth is, if we understood what Compass was doing correctly, it would be really strange to have somebody with a very, very long criminal history, like lots of different past, sometimes over 20 past crimes. And then you look at the Compass score and it's very low risk. You're thinking, well, I'm not sure if that's right. It looks a little strange.
Absolutely. Worth deeper examination, if nothing else, right?
Yeah, but it's really hard to deeply examine something that's proprietary, and that's the problem.
Well, when it comes to interpretability, obviously we kind of always want that, but what about, I don't know, someone who says, gee, the state of the art, even though it's a black box, it's doing incredibly well. It can pick out these medical diagnostics at or better than the doctor level. Do we really still need interpretability there?
Well, you have to ask why. Why is this thing picking up things that the doctors aren't picking up? And to be honest, in healthcare, most of the time the reason is confounding. It's picking up on something that it really shouldn't be using, information that would be really quite bad to use. So there have been a bunch of studies recently. One of them in particular was really interesting, where the machine learning model was super accurate in looking at x-rays and figuring out which patients were going to have good outcomes or bad outcomes. And then the doctors realized why the model was doing so well. And it's because some of the patients had gotten x-rays that were from a portable machine, and some of them had gotten the x-rays from the regular machine. Now, if you think about it, who are the patients who are getting the x-rays from the portable machine? They're the patients who couldn't make it to the regular machine. So the machine learning model was looking at whether the x-ray said that it was portable or not. It was just looking for the word portable in the x-ray and not looking at the actual content of the x-ray, the medical content of the x-ray image. And so you think about it, especially in healthcare, because there's confounding everywhere, right? Patients who are sicker get different treatment than patients who are less sick. Just happens all the time. And so, you can say, hey, guess what? This machine learning model is super accurate. But if you don't ask why, you could be in a lot of trouble. It might not generalize at all to new settings.
Yeah, definitely. We do need the models to do more than say, because I told you so, or because that's what I think. There are a couple, levels to interpretability. Could you share maybe your perspective and experience on how helpful a model can be? What can it do to build trust? Let me know that it's come up with the solution by some mechanism I believe in.
Well, interpretability means something different in each different application domain. So you can have these applications where the data are a structured table, like you have each patient and you have all of their past conditions, and then you're trying to predict a future condition. And in those cases, you might want to look at something like decision trees or scoring systems, which are sparse linear models with integer coefficients. So these are models with just a few conditions or a few things that you add up as like a doctor or something. You would add up a few scores and then produce a prediction. And those types of models are very commonly used in medicine already. And the idea here is that since doctors are already familiar with these types of models, maybe you can design a machine learning method that produces models that doctors are already familiar with, that people already like. These types of models have been used for 100 years. So why not design a machine learning method to build models like that? And then in other domains, like for instance, in computer vision, it's much harder to figure out what interpretability actually means. And so what we've been trying to do in our group is to try to imitate the way humans explain things to each other on very difficult computer vision problems. So for instance, we've been using this bird watching data set where you're trying to distinguish which, you get a picture of a bird and you want to know what type of bird it is. And the question is, how would a human describe to another human what kind of bird that is? And what they might do is they might say, well, this part of the bird looks like this other part of this other bird that I've seen before. And look, these are similar to each other. And that's why I think that this bird is clay-colored sparrow or whatever. And so, like I said, it depends on the domain. But one thing I can tell you is that I've worked in a lot of different domains. I've worked in healthcare power grid reliability. I've worked in criminal justice, in computer vision, in all these different domains. And we've never found a case where you really had to sacrifice accuracy to gain some level of interpretability. Like you can always add some kind of interpretability constraint to your model and still maintain the performance that it had before. So I don't see a good reason why you shouldn't try to add interpretability, although I do admit that it's harder to train a model that is interpretable than one that isn't, just because, you're adding extra constraints.
Is there a component as well of maybe labor costs, that it's pretty easy for an intern to pump and dump a model these days out of some CSV, but to truly have some ingenuity and to look at it and apply various tests and methods and ensure that you build a model that is also interpretable and that we trust those interpretations? I think that maybe takes more expertise. Could it be a shortage of the right talent to do it?
Yes, there is definitely a shortage of the right talent. And also, it's very hard for researchers to make kind of industrial strength interpretable modeling code. So it's a combination of those two things. I mean, there's also another reason driving the black boxiness of code. It's because people like black boxes. They love the idea that these complicated algorithms can uncover secrets in data that you wouldn't normally be able to find. And they're even so interesting that you wouldn't be able to understand them. I mean, so that's one thing that people love about them. But another thing people like is that it's hard to steal a secret that is complicated, right? If you actually need a piece of code to make a prediction, well, hey, that keeps our secret, right? If we find out that our whole model is actually just as good as a simple point scoring system, yeah, I'm not sure what the business model is there. So, I mean, there's a number of reasons that people really like black boxes, but for some of these high stakes decisions, there's not really a good reason to use them.
Thanks to this week's sponsor, Brilliant. Brilliant is an interactive learning tool that I like very much, and I think you will too. If you head over to brilliant.org/dataskeptic, I actually recommend that. Do that now. Pull up, there's a great video there that walks you through some of the stuff they have, showing me this algebra test and some fun ways that people can build programs in the browser. This looks like good stuff I might be able to get my nephew into. I didn't know they had fun stuff like that. I'm used to going down and doing these courses or doing the problem of the day. I have a policy called leave a tab open for Brilliant. Just sit there and I need a little coffee break type thing. The courses are divided up into nice sections to do that. In particular, I've been going through the group theory course here on the stay-at-home order. There's an interesting group theory problem that's a pretty advanced thing I want to get into, and having this course has been really helpful for prepping up for that battle. So I'm grateful to Brilliant, and I think you guys should check it out as well. Head over to brilliant.org/dataskeptic so they know we sent you. Once again, brilliant.org/dataskeptic. Interesting. So that there is a perceived gap that maybe it's not a real thing, but especially hearing some of your experiences, but people in industry will tell you that, there's a trade-off here. And yes, it'd be nice to be interpretable, but we're profit driven. I've got to get a maximizing of accuracy. It sounds like you would think that's a cynical perspective. How else might that person reframe their view of the world and embrace a little interpretability in their ML?
Well, they usually wouldn't be that direct about it, would they? I don't think.
Perhaps not. Yeah.
I think they mostly just say, "Oh no, we couldn't create an interpretable model. We need to explain our black box. We've decided to use this black box, and now we have to figure out how to explain what it's doing." And if you ask them, "Did you ever try to replace it with something with a model that you understand?" They usually say, "No, we didn't try that." Yeah, I've embarrassed a few people that way. I've been in talks where somebody's giving like a research talk in front of a large audience, and I asked this question, "Hey, did you try, rather than explaining that black box, did you try running an interpretable model?" And they sort of think, "Oh, I don't know. No, we didn't."
Well, it very much falls in line with the experience you had at the Explainable ML Challenge, if I'm reading correctly. Maybe to start, could you introduce what was the Explainable ML Challenge?
Yeah, so this was something that I heard about, and we took a look at it. The idea was that we had some data. The data was from FICO, and it was about individuals who were applying for loans. And you would get a very large number, thousands of these data records that were supposed to represent people applying for a loan and then whether or not they defaulted on their loan. And this was a particularly difficult group of people. About half of them defaulted and half of them didn't. And your job was to design a black box and explain it. And we thought, "Oh, yeah, let's give this a try. This looks fun." And then within a few days, my students noticed immediately that you actually didn't need a black box for this data set, that you could do just as well with an interpretable model. And so we had this debate, like, what should we do? We're going to lose the competition if we don't follow the directions, but we just don't think we want to follow the directions. We can just send them an interpretable model and let's do some nice visualization with it and show people what it looks like and so on. That's what we ended up doing. And the judges, we were right that the judges would have no idea what to do with the model we gave them. And they didn't. They had no clue what to do with it. Yeah, so we didn't score at all in the judging. We did really poorly. And so as it turned out, the judges actually thought about it when I said to them, "Hey, look, you guys need to rethink this." And they actually took a look at it and they actually created a separate prize for us. It was the FICO Recognition Award. They invented this award, this FICO Recognition Award, for the work that we did, giving them something that was not expected.
Do you know, were you the only entry that didn't follow the rules, I guess is maybe the way to put it?
I'm not sure. I mean, I think maybe there might have been one other one. Now that I think for the most part, people followed the instructions of the competition. I mean, people usually don't second guess when they've given a set of instructions for the competition. Usually the competition's well structured so that if you follow the rules that you'll place well. And so the people designing the competition, they didn't think that you could get an interpretable model out of this data set. And so a lot of people didn't think that either.
And if instruction one is build a specifically black box model, well, then one can follow that direction. You said yours did just as well. Could we unpack that maybe in terms of some of the standard model diagnostics? Even if those don't tell the full story, how do they compare on that level?
Oh, it's really simple. They were all about 73 or 74% accurate.
So within a very small margin.
Yeah, and ours was 74% accurate.
I don't know if you believe this notion. I'm going to take that maybe you don't, but people will say, hey, there's a trade-off between interpretability and accuracy. In this anecdotal case, can we quantify that trade-off in any way? Is it 0.5% or what do we get out of it?
No, there's no trade-off at all. I mean, our 74% was the best we could do. And I have students who are working on this who are experts in neural network learning and all kinds of other stuff. No, the 74% is the best you were going to get with that data set. And in fact, that interpretability accuracy trade-off, it's really a myth, and it's a very harmful myth as well, because in most cases it goes in the opposite direction. Actually, interpretability helps you with accuracy. And so the way that works is that if you design an interpretable model, you start second guessing it and you start thinking about it going, are these factors really the most important factors? Are these really the factors that should be making the predictions? And then you think to yourself, well, maybe there's something wrong with my data set because these factors probably shouldn't be as important as they are. Or you think to yourself, well, if these factors are important, maybe I should build more features for my model that are like this. And so you end up gaining accuracy as a result of interpretability, because once you start editing your data and doing more data science, you're actually gaining performance.
And I'd love to know a little bit about the interpretable qualities of the model you guys built. So maybe we could start with what are some of the features that we're distinguishing in its decision-making process?
For each observation, whenever there's a prediction made, it tells you exactly what features caused that prediction to be made. So for each person, you find out what exactly the key factors were that drove that prediction.
Gotcha. So it was on a case-by-case basis, almost like a good loan officer who was reviewing these and taking all the details into consideration?
Exactly. It'll say something like, well, your external risk estimate subscore is really high, and here's the value you got. This is in the very top group of individuals, and so you got this many points for that. And then you were delinquent on your trades. Here's how delinquent you were, and this is how much it contributed to your score.
And did you have a chance to get any feedback from the FICO team? Do they find these explanations intuitive?
Yeah, they do. I mean, they were interested in talking with us further, so hopefully that'll happen sometime. I should probably enhance my answer to one of the previous questions you asked. We were talking a minute ago about how interpretability can help you build accuracy. I should probably talk to you about how I got interested in interpretability in the first place. I was leading a team in New York City. We were working with Con Edison, the power company, and we were trying to predict power grid reliability. And in particular, we were trying to predict fires and explosions and smoking manholes that happen on the low voltage power grid that goes underneath all the streets and all the avenues in the boroughs of New York City. And the data was very, very challenging to work with. It was like trouble reports, which were typed by dispatchers, and it was accounting data that dated back to the time of Thomas Edison, back to the 1880s. It was very, very difficult to work with. So just even trying to figure out which cables went into which manholes was really hard. So just the quality of the data was just really a challenge. And when we started building these models, they were really bad. And there was one embarrassing situation where we told Con Edison, hey, this manhole, you might want to check out this manhole. And then they went into the manhole and they're like, there's nothing wrong with this manhole. It's totally fine. And we were so embarrassed. I was embarrassed. And so I went back and I thought to myself, we really need to rethink this whole thing. And so that's when we really changed strategy. We started trying to read the trouble tickets automatically and put them into our structured database and do really high quality data processing and try to tune our data processing towards the parts of the database that were most influential in the predictions. And then from there, we were able to get very high quality predictions to the point where in our blind test, we were able to predict most of the manholes that had fires or explosions within the top few percent of our rank list. So it was really a matter of insight driving the quality of predictions. And so that's when I thought, look, when I tried all these different machine learning methods on the raw data, I wasn't getting anywhere. They were all equally bad. and they were all bad enough that you would never want to use them. And when you all of a sudden started doing real data science, like looking at the insight that these models were giving you and understanding what the models were doing, then all of a sudden the quality of your predictions was going up tremendously.
Very interesting. And I'd love to hear a little bit more about that process, if you don't mind. I think a lot of people are in a similar state where they just tried to throw the kitchen sink of algorithms and didn't get them anywhere. And now they've really got to dig in and understand the data and maybe formalize it in some better way. Do you have any advice for how to do that exploratory analysis?
So it really depends on what problem you're working on. But for most structured data problems, exploratory data analysis is so totally underrated, and I don't know why. So I used to teach introductory statistics at MIT. I would always tell my students that my favorite tool was the histogram. If you just plot a whole bunch of stuff, you actually get to know the data pretty well. It's amazing how much insight you can get from just plotting histograms and just doing basic plots. Most people try to, send in the neural network. Oh, I got a data set, send in the neural network. No, that's not how you should do it. So exploratory data analysis is great, plotting all kinds of relationships. And also some tools from data mining are really also underrated. It's shocking that people don't even teach association rules. I don't know why people don't teach these.
Like a priori algorithm and that sort of stuff?
Yeah, exactly. Like the a priori algorithm. I don't know why people don't teach that anymore because it's so crazy useful. And we do a lot of exploratory data analysis just using a priori and similar algorithms.
There was one insight from your paper that really stood out for me, that black boxes can actually mask mistakes. Could you help me dig into some of the ways in which that'll happen?
Well, confounding is one major one, especially for healthcare data. If you have, like I said, any kind of weird confounding, the algorithm can use that to help it create better predictions, but you won't necessarily realize it. So that's one way. Other ways are things like typographical errors, right? You won't be able to tell if you have a typo in your input if you just throw the input into some complicated function and look at the output. Like you won't see it. Also, things like feature importance get completely lost with black box models. So for instance, if you take a model, let's say it's a model for criminal justice risk scoring, okay? So this actually happened. So I'm telling you a story that's actually real. So there's a famous reporting group called ProPublica, and they took the scores from this black box model, this COMPAS model that I was telling you earlier, and they tried to create a proxy model for COMPAS. So they tried to sort of recreate COMPAS, and they built a linear model that was supposed to approximate COMPAS, and they looked at that model and they said, oh, it depends on race. Therefore, COMPAS depends on race. The problem is that they did their analysis wrong. As it turned out, race was correlated with age. And if you actually go back and sort of figure out how the black box model depends on age, which is something we actually did recently. So if you go back and figure out how that black box model depends on age and subtract out the correct dependence on age, then all of a sudden the dependence on race disappears. And so this whole article that got huge amounts of publicity and people trying to reproduce it and all this other stuff was all wrong. The analysis, the technical analysis was all wrong. You have to really be careful about the way you analyze black box algorithms and even just the way you interpret what they're doing, especially with feature importance.
Something like COMPAS is especially disturbing because there's only one choice. There's no market for it. Like if Amazon's recommender system recommends me things I don't want, I just won't buy them. It's their loss. But if I go to court for a crime, I can't really shop around in the same way. Do you have any thoughts on the proper way these things should be done? Should COMPAS be open source? What are some better methods for not having these concerns that decisions are made by black boxes that affect people so deeply?
Well, there are a whole bunch of criminal justice risk scoring models. And to be honest, they're all about equally accurate. And they essentially depend on just age and numbers, counts of past crimes. You don't need something complicated for this particular problem. It's unnecessary. And then if a judge has a very simple model, if you have like 3 points for this and 3 points for that and 2 points for this, then the judge can combine that information with all of the stuff that's not in the database. Like, okay, did this person get their high school diploma? Did the person take classes while they were in prison? Did they take classes that would help them get a job in the future? And you can combine that information with the criminal record history information and then come up with some kind of risk that would actually determine a reasonable parole decision that somebody could argue with.
The ability to kind of probe it and ask questions is interesting too. If the model, as you say, were some simple rules, it wouldn't be hard for the legislator or the public to debate about it. But when it's a black box and one we can't even probe very effectively, that puts up some challenges. Do you see this as something that's maybe just going to be figured out because some of this technology is so new, or is there going to be some sort of civil movement that has to take place where the public helps specify a little bit about the ways in which government and people like that should be applying machine learning and these sorts of tools?
In the case of Compass, the technology is not new. I think Compass itself is actually a fairly simple model. It's just that it's proprietary. I don't think that it was designed with a fancy machine learning tool at all. But like I said, if you did use a fancy machine learning tool for interpretable modeling, you'd get a very, very simple model and you could just replace Compass with it. So I think it's a political question, you know? You have to have some mechanism to say, look, do I need this complicated of a model? Can I have a simpler one that predicts just as well? There's a principle that we haven't talked about that I should probably mention, which is this idea of the Rashomon set. The Rashomon set is the set of models that are all about equally good. Okay, so you have a finite data set, and there could be 10,000 equally good models, some of which you'd want to use and some of which you wouldn't. You know, if that Rashomon set is really large, then hopefully you can find a model in there that you actually want to use. So for instance, with the criminal justice case, you have Compass, which is equally good. It's maybe very complicated, maybe overly complicated, but there could be another model in the Rashomon set that's equally good that is nice and simple. So the fact that the Rashomon set is so large allows these different models to exist, and then people can kind of choose from within them which model they actually trust or which model they actually want to use. So I think we should make sure that people know about this Rashomon set. You don't want them to just take a model at face value. You want them to understand that this is not the only model out there that predicts that well, that there's a whole class of models that predict that well, and they have a choice. And so should we use a model that's complicated? Well, can you find a simpler one that's just as good? Is there another one in the Rashomon set? And that's something most people don't understand. So we need to get that out there.
Absolutely. Another possible, I don't know if culprit's the right word, but maybe you can tell me if you think there's any blame or whatever to be assigned here, but I find the existing suite of machine learning tools to be very well engineered and kind of frictionless if you're doing typical stuff. So if I just have some tabular data loaded up, I can build a model in 10 lines of code. There's a lot more effort going into doing something that's interpretable or producing all those histograms along the way as I study what the model's learning. Do you think maybe the tooling could partially be to blame for why engineers don't do more of this type of work?
Well, engineers really should be doing that exploratory data analysis because, like I said, you could have a black box model that depends on confounding factors that you don't want. So there's no excuse for not doing good data science. And it's possible that using the interpretable models is just as seamless as using some of the standard toolbox. So for instance, you could use CART, which is a decision tree algorithm. CART is an old algorithm. It was designed in STEMs in the 80s and early 90s. But, you know, computers have increased their speed a million times since then. And so if you grab the OSDT package or the Corals package, which are more modern decision tree methods, then you might be able to get just a model that is simply better with no sacrifice. And so we just got to get these tools out there. We got to get them into the standard toolbox. We have to start teaching them.
And what do you say to the argument that person could say, okay, well, for some problems, yes, there are these simple variables. Maybe you can learn about medical diagnostics or this or that, but there exists some class of problems that maybe that person knows about. Perhaps it's the stock market, I don't know, where they say this class of problems is so complex, we must have black box models. Do you think such a class exists?
I've been trying to find one. I've been really trying so hard. Our latest attempt is in material science. I was approached by the chair of material science at Duke. Her name's Kate Brinson, and she's absolutely brilliant. And I thought, maybe I've met my match. But even there, I have a wonderful student who was able to find interpretable machine learning models that do just as well as the black boxes. And they're incredible. They find these patterns that you wouldn't notice with your eye, but that once we point them out to you, it's like, oh yeah, I kind of see that. Yeah, I get it. Now I can classify these complicated materials. So even there, I haven't found it. So I'm really curious whether it'll show up. But the fact is that if you consider this massive amount of healthcare problems, computer vision problems, power grid reliability problems, criminal justice problems, if you consider all these problems that we know interpretable models exist for, then it seems kind of like, okay, how many more domains do we need to search for to try to find these mysterious problems where you need a black box?
Sure. Yeah, that is a strong shifting of the burden of proof. I would agree on that.
Well, one thing we didn't discuss is, explanations of black boxes versus building models that are interpretable in the first place. And, one of the main problems with doing that is that, like, if you try to build an explanation for a black box, you're essentially giving more authority to that black box. Whereas, you say, oh, I can use the black box because I can explain it. But the truth is you didn't need the black box in the first place, so why are you explaining it?
Yeah, that's an interesting point. It's a sort of shifting of the goalposts, that if the model's interpretable, then I trust its interpretations and extend my trust as far as I follow them. But if it's black box, it's kind of sneakily claiming correctness, guilty until proven innocent, I guess? Or innocent until proven guilty. I got it backwards.
Well, it's sort of saying, oh, it's okay. You can trust me. Even though I'm a black box, I can be explained. And it's like, well, you could have gotten your feature importance wrong. You still had to go and compute a complicated function, and there still could have been a mistake in the input that would be hard to track down. So all of these things still are a problem when you talk about black boxes with explanations. And that sort of diminishes when you use a model that's interpretable in the first place, because the explanations are exactly what the model is computing.
On your first reading of their work, before doing any analysis of your own, did you find the explanation that ProPublica provided for the black box to be compelling?
Oh, no. When I read ProPublica's article, this was 6 months after we had published our paper in the Journal of the Royal Statistical Society on interpretable models for recidivism prediction. So we had just published a paper that said exactly the opposite of the ProPublica study. It basically said, you don't need a black box model for recidivism prediction. And we also wrote down that we don't need to use race, and we're not losing any accuracy when we omit race. So when the ProPublica article came out, I was like, either they're wrong or we're wrong. And I don't know which one it is, so I'm going to go check it out. And it turned out that they were wrong. And so they didn't realize that when you approximate a nonlinear model with a linear model, that you can get the wrong interpretation. They were just thinking in this very linear, standard way, but that way is incorrect. So when I read their article, I was thinking, first of all, you don't need a black box. Second of all, it doesn't depend on race. That's what I was thinking when I read it. And then I just sort of put it down. I just thought, oh, they're wrong. Nobody's going to listen to it. That's what I actually thought. And so, then it went wild. And I thought, oh, I got to go figure out what's going on here. So that's when we started investigating what was actually inside the black box and trying to figure out what went wrong in ProPublica's analysis.
Well, I'm glad you and your collaborators did. It's an important discussion to this very significant modern topic.
Yeah, and it was pretty fun actually to work on, because we kind of wanted to know what was in this secret model anyway. We wanted to know what the nonlinearities were and how it depended on age and so on. So that was pretty fun for us to try to figure that out from the data. It was like data detective work.
Having done that, obviously you have some semblance of how that model works, but you don't know it exactly. You didn't break into the Compass building and look. If you did, how close do you think your perspective of the model would match what the actual model does?
I think we made a lot of inroads on age. I think we kind of understand a lot about how the model effectively depends on age. And we got somewhere in criminal history, but not all the way. And then we weren't able to get anywhere else because we didn't have data for anything else. But luckily for us, age and criminal history are the most important factors in these models. So that was kind of nifty.
Well, this has been really great. Thank you so much for coming on and sharing your work. Where can people follow you online?
Oh, you can just Google me and go to my website.
All right, we'll have a link to that in the show notes as well. Yeah, thanks again for joining me today.
Yeah, my pleasure.
Thanks for listening to another episode of Data Skeptic Interpretability. And thanks to our sponsor, Brilliant.org/Dataskeptic. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich. Thanks, everyone. See you next time.
What